So far, we have used regression to test linear associations between our explanatory variables and our response variable. By linear, we mean that the association can be explained best with a straight line. Here is a scatter plot showing a linear association between urban rate and internet use rate from the Gapminder dataset. That is, we can draw a straight line through the scatter plot, and this regression line does a pretty good job of capturing the association. But what if the association is not linear? That is, what if the association is curvilinear? For example, take the relationship between anxiety and performance. It is a well-established phenomenon that both low anxiety and high anxiety are related to poor performance, but that a moderate level of anxiety is optimal to perform at your best. If you drew a straight linear regression line through these points, most points would be really far away from the line, meaning that there is a lot of prediction error. The best fitting line is not straight. Rather, it is one that curves to capture the nonlinear nature of the association. Here is an example of a less extreme curvilinear association between urban rate and female employment rate with a linear regression line. Returning to the Python script for the Gapminder dataset, the code to produce this scatter plot is here. Here we are creating an object called scat1 that will be our scatter plot. We then use the seaborn regplot function to plot our explanatory x variable, urban rate, and our y response variable, female employment rate, separated by a comma. Note that the variable names for both variables have quotation marks around them. After another comma, we add scatter equals true to tell Python to plot a scatter plot, and then we tell it which dataset to use. You can see that it looks like female employment rate decreases as urbanization rate increases, but that around urban rates of 80 or higher, it looks like female employment rate appears to increase. So it looks like kind of a U-shaped association. Just like with the anxiety and performance association, a straight linear regression line isn't doing a good job of picking up the curvilinear part of the association. We can actually fit a line that curves to better fit the association by adding a polynomial term. For example, we could add a second-order polynomial or quadratic term to draw the line of best fit that captures the curvature we are seeing. To do this, we use the same seaborn regplot function code that was used to draw the scatter plot with a linear regression line. The difference is that we add some additional code within the parentheses for the seaborn regplot function. We add order equals 2 to ask for a quadratic line that includes the second-order polynomial. If we run the code for both the linear and quadratic scatter plots at the same time, we will get a single scatter plot with both the straight linear line and the curved regression line. Now my scatter plot shows the original linear regression line in blue and the quadratic regression line in green. Notice how the quadratic line does a better job of capturing the association at lower and higher urbanization rates. The points at these levels are closer to the quadratic or second-order polynomial curve, meaning that the expected or predicted values are closer to the actual observed values. So based on just looking at the two curves, it looks like the green quadratic curve fits the data better than the blue straight line. But we can be even more sure of this conclusion if we test to see whether adding a second-order polynomial term to our regression model gives us a significantly better fitting model. I do this by simply adding another variable that is the squared value of my explanatory x variable, x squared, to my regression model. First, let's test a regression model for just the linear association between urbanization rate and female employment rate using the OLS function from the Stats Model API formula library. Note that we have centered our urban rate quantitative explanatory variable, urban rate underscore C. Centering is especially important when testing a polynomial regression model because it makes it considerably easier to interpret the regression coefficients. If we look at the results, we can see from the significant p-value and negative parameter estimate that female employment rate is negatively associated with urbanization rate. So the linear association, the blue line in the scatter plot, is statistically significant. But the R-square is 9%, indicating that the linear association of urban rate is capturing only about 9% of the variability in female employment rate. But what happens if we allow that straight line to curve by adding a second-order polynomial to that regression equation? The Python code to do this is here. As you can see, it's the same code as for the linear regression model with the exception of some additional code. Specifically, if you look at the formula, you'll now see that we have added another term to the model, that is the square of the urban rate explanatory variable. Stats model uses Patsy formula language, which is what we include inside the quotes when we name our response and explanatory variables and any other variables we want to include in the model. Patsy provides a built-in function, I, called the identity function, that simply returns the input of what's in the parentheses. So in this case, the I, urban rate star star 2, returns a variable that is urban rate raised to the power of 2, that is, urban rate squared. This term is our second-order polynomial, or quadratic term. When we look at the table of results, we see that the value for the linear term for urban rate is negative, and the p-value is less than 0.05. In addition, the quadratic term is positive and significant, indicating that the curvilinear pattern we observed in our scatter plot is statistically significant. A negative linear coefficient and a positive quadratic coefficient indicates that the curve is convex, such that it starts high, then goes down, and then starts to go up again. This is consistent with the bowl-shaped pattern. This is consistent with the bowl-shaped quadratic curve we saw earlier in our scatter plot. In addition, we see that the R-square increases to 0.16, which means that adding the quadratic term for urban rate increased the amount of variability in female employment rate that can be explained by urbanization rate from 9% to 16%. Together, these results suggest that the best fitting line for this association is one that includes some curvature. Note the two warnings in the output. The first warning is simply reminding you that the estimation of the standard errors assumes that your regression assumptions are met and that your model is correctly specified. The second warning indicates that there are variables in the model that are highly correlated with each other. This is an indicator of multicollinearity, which can create some instability in the estimation of the parameter estimates and make it difficult to interpret them. Ordinarily, if we have two highly correlated explanatory variables, we would want to put only one of them in the model. Obviously, the second-order polynomial, which is urban rate squared, is correlated with urban rate. However, in this case, we want to keep it in the model because we specifically want to capture the curvilinear relationship that was evident in our scatter plot. This brings us to another important characteristic of centering. Centering significantly reduces the correlation between the linear and quadratic variables in a polynomial regression model. We can also test for more complex nonlinear associations by adding higher-order polynomials. For example, you can add cubic, third-order polynomial, or even quartic, fourth-order polynomial terms to the model to account for more complex curves. For example, this scatter plot shows more than one curve. In this case, adding a cubic, or third-order polynomial term, might improve the fit of the model. One thing to keep in mind, though, is that modeling more complex curves in the sample data will often improve the fit of the model for that sample. However, it also increases the risk of doing something called overfitting. Overfitting occurs when you get a model to explain your response variable really well in the sample, but that model becomes very specific to the sample data. That is, it capitalizes on the variability that's present in that sample. The downside is that an overfitted model that fits the sample really well may not fit well at all on another sample drawn from the same population. An overfitted model is biased toward the sample it was developed on, and consequently, the conclusions we draw from that model may not be representative of the population. So we try to establish balance, where we identify a model that fits our sample well, but will also fit well if we tested it on another sample from the same population. This is called the bias-variance trade-off, and we will discuss this in more detail in the fourth course of the specialization, Machine Learning for Data Analysis.